Warm welcome to yet another discussion on GATE Electronics and Communication Network related papers. Today we are checking GATE 2007. Moving to the first question. An independent voltage source in series with an impedance ZS equal to RS plus JXS delivers a maximum average power to a load impedance ZL when ZL equal to, right? So it's a direct application of maximum power transfer theorem. So the load impedance must be, ZL must be equal to RS plus RS minus JXS, right? So the answer is D. The RC circuit shown in the figure is, right? We have to select which type of filter is this RC combination is, right? So it is better to apply two extreme ends of frequencies. That means at omega equal to 0, the circuit looks like this. A resistance R is there. At omega equal to 0, the capacitor behaves as open circuit, right? Next, again another RC and again capacitor behaves as open circuit. So, output is taken across these two terminals, V0. That means V0 equal to 0. Because there is an open circuit in this path, V0 turns out to be 0. Similarly, we can check another extreme case also, that is omega equal to infinity. For that, capacitor behaves as a short circuit, right? So capacitor behaves as a short circuit at this point. Next, a R is there and a capacitor, short circuited capacitor is here, right? So again, the output V0 turns to be 0. Because the resistance is bypassed by a short circuit, so all current will flow through this path and the output turns out to be 0. That means for omega equal to 0, output V0 equal to 0. Similarly, for omega equal to infinity, V0 equal to 0. So, as low frequency, it does not conduct. Similarly, at high frequency also it does not conduct. That means it is not at all a low pass or a high pass filter. Now option seems to be band pass or band reject filter. It is also not a band reject filter because a band reject filter can reject only a particular frequency, right? So here it means that it is just a band pass filter, right? So option C, a band pass filter. Moving to a 2-mark question. Two series resonant filters are as shown in the figure. Let the 3 dB bandwidth of filter 1 be B1. Right, filter 1 is this, and the 3 dB bandwidth of the filter is B1. Similarly, filter 2 has bandwidth of B2. Now we have to evaluate what is B1 by B2, right? So we know bandwidth of a series RLC circuit is given by R by L, right? I repeat, bandwidth of a series RLC circuit is given by R by L, right? So for the first case, bandwidth of the first filter is R divided by L1, right? For first filter. Similarly, for the second filter, bandwidth is related by R divided by L2, but L2 equal to L1 by 4 or 4R by L1, right? So we have to evaluate B1 by B2. So that turns out to be R by L1 into L1 by 4R, right? So that is 1 by 4. So answer turns out to be D, 1 by 4. Moving to another 2-mark question. For the circuit shown in the figure, the Thevenin voltage and resistance looking into the points X, Y, R, right? So here we have to evaluate Thevenin voltage and Thevenin resistance. So it is easier to take node equation at this node, right? So I am marking this node as A and it is same as VThevenin, right? VThevenin voltage is the voltage across XY terminal. So I am marking VA. VA in times turns out to be VThevenin. So directly I am taking VThevenin. So VThevenin by 1 ohm, right? VThevenin by 1 ohm plus again VThevenin minus 2i, right? Minus 2i by 1 plus VThevenin by 2, right? VThevenin by 2. And the 2 ampere current is entering, that means it is on right hand side. Now we can substitute what is 2i. I turns out to be, I is the current flowing from this point to this point. So I equal to VThevenin by 1, right? So I am substituting and taking common VThevenin. V Thevenin into 1 plus 1 minus 2 I equal to V Thevenin. So minus 2 only plus 1 by 2 equal to 2. So V Thevenin into 1 by 2 equal to 2, or V Thevenin turns out to be 4. So V Thevenin is 4 volt. Now we have to evaluate Thevenin resistance, right? For calculating Thevenin resistance, we have to deactivate all the independent sources. Here a 2 ampere current source is there. For deactivating it, we have to open circuit it, right? Then again the dependent source is there. So the calculation seems to be a difficult one, but it is much easier if we apply a short circuit here and evaluating Thevenin resistance RTH as open circuit voltage by short circuit current. Open circuit voltage is actually we evaluated as Thevenin voltage, right? Because it is the voltage across XY terminals when the terminal is open circuited, right? So V Thevenin by ISC or I short circuit, right? So we have to evaluate the short circuit current flowing through this terminal XY, right? For that, if I made a short circuit, all the 2 ampere current must flow through this XY terminals, right? No current will enter 2 ohm or move on to left hand side. So short circuit current turns out to be just 2 ampere, right? Now Thevenin resistance RTH equal to 4 by 2, that is 2 ohm. So answer turns out to be D, 4 volt 2 ohm. Moving to another 2 mark question. In the circuit shown, VC is 0 volts at t equal to 0 seconds. So that means initial voltage VI or V initial voltage VIV equal to 0. For t greater than 0, the capacitor current IC of t, where t is in seconds, is given by, right? So it is a direct application of capacitor charging discharging expression, that is V capacitor voltage across capacitor equal to V final minus V initial e raised to minus AT, right? For this case, we have to check what will be the final voltage across the capacitor, right? So there is a plus or minus 10 volt is there, 20 kilo ohm is there, again another 20 kilo ohm is there. As capacitor behaves as open circuit during steady state condition, the voltage splits into this 20 kilo ohm and another 20 kilo ohm. So voltage turns out to be just 5 volt. So V final value equal to 5 volt. Now applying these values, 5 minus 5, initial value is 0. So e raised to minus AT. Now we have to evaluate what is A. A equal to 1 by time constant. Here it is a RC circuit. So 1 by RC. R turns out to be 20K parallel 20K. For evaluation of R, we have to deactivate the voltage source. That means it have to be short circuited. Now the resistance turns out to be 20K parallel 20K. That is 10K, right? 10 into 10 raised to 3 into capacitance. Capacitance is 4 into 10 raised to minus 6. So simplifying, 10 raised to 3 or 1000 divided by 40. 1000 divided by 40 is 25, right? Now we can substitute A, that is 25T, right? 25T. This is actually the capacitor voltage, but we have to evaluate the capacitor current, right? We have to evaluate the capacitor current. Capacitor current is given by I equal to C into dV by dt, right? So capacitor value is 4 into 10 raised to minus 6 into derivative of this value. That is derivative constant is 0 minus 5 into minus 25 e raised to minus 25t, right? That is 4 into 5, 20. 20 into 25, that is 500. 500 e raised to minus 25t microampere or equal to 0.5 e raised to or exponential minus 25t milliampere, right? So checking options, it is A. Answer is A. Moving to another 2 mark question. In the ECE network shown in the figure, the phasor voltage VAB is, right? We have to evaluate the voltage across this phasor, right? So either you can apply current division rule or can apply node analysis. Anyway, I am applying node analysis. So voltage across AB is, that means VAB by the impedance, that is 5 minus J3 plus VAB divided by 5 plus J3, right? 5 plus J3 equal to 5 angle 30 as this current is entering to the node. Now taking common VAB and multiplying by complex conjugates, that means 5 plus J3 on denominator side it is 5 minus J3 into 5 plus J3, that is 25 plus 3 square is 9. Again here 5 minus J3, right, equal to 5 angle 30. That is VAB into 5 plus J3 plus 5 minus J3 is 10. 10 divided by 25 plus 9 is 34, right, equal to 5 angle 30, or VAB turns out to be VAB equal to 5 or 34 by 10. 34 by 10 is 3.4. So 5 into 3.4 angle 30 degree. So 5 into 3 is 15. Now 5 into 0.4 is 2. That means 17 angle 30 degree. So answer is D, right? D. Now moving to another 2-mark question. A load of 50 ohm is connected in shunt in a 2-wire transmission line of Z0 equal to 50 ohm as shown in the figure. The 2-port scattering parameter matrix of the shunt element is, right? So we have to evaluate the scattering parameter matrix of this shunt element, right? So in terms of impedances, scattering parameters is as given. S11 equal to ZL parallel Z0 minus Z0 by ZL parallel Z0 plus Z0, right? So we have to directly substitute the values. Here the load impedance is 50 ohm and characteristic impedance is 50 ohm. That means 50 parallel 50 is 25. 25 minus 50 divided by 25 plus 50, right? That is minus 1 by 3. S11 equal to minus 1 by 3. Similarly, we can evaluate S21 or S12, right? Here S12 equal to S21 because it is a reciprocal network, right? Looking from left and similarly looking from right, it seems to be same. So it's basically a reciprocal network. So for reciprocal, 2 into ZL parallel Z0, right, divided by the same denominator, that is ZL parallel Z0 plus Z0. So that turns out to be denominator is anyway 50 plus 25, that is 75. On numerator side, ZL parallel Z0, that is 25. 2 into 25, 50. So that turns out to be 2 by 3. Right? Now we have to evaluate S22. S22 equal to, again, ZL parallel Z0 minus Z0 by ZL parallel Z0 plus Z0 in this case. Right? So again same values. ZL parallel Z0 is 25. 25 minus 50, that is minus 25 by denominator is again 75, that is minus 1 by 3. So the answer turns out to be minus 1 by 3, 2 by 3, 2 by 3 and minus 1 by 3, right? So option C, right? Minus 1 by 3, 2 by 3, 2 by 3, minus 1 by 3. So for more GATE tutorials, subscribe my channel. Now I am signing out till we meet again with another GATE paper. Thank you.